So we've talked about the different types of structural systems, but there are some other features that are important when we're choosing the structural system of a building. So let's talk about what other features we look at, particularly related to earthquake design. So one of the things we're interested in when we do seismic resistant design is the ductility of the system we're using. Through observation of past earthquakes, engineering, we begin to see what types of things typically survive earthquakes better than others, and what are the common features that some of those structures have. The material used and how we use it really affects the survival rate of a given building or bridge. And it's on a material level, it's really the ductility of the material that seems to improve the survivability. Ductile materials are going to be those that can deform severely, but still maintain their strength. Some mild steel, for example, perlite, is a very ductile material in the fact that once it yields, it can still resist a relatively large force, even while it deforms. Brittle materials, on the other hand, they may be strong, but they fracture with limited deformation after they've reached their peak strength. For example, high strength steel, such as a martensite, is a very brittle type of steel. So how does that work in an earthquake? Let's consider a very simple structure. We've got the ground on wheels. We've got a mass on top of that. And what's connecting this mass to the ground and the wall is just a simple truss link in tension or compression. And we're going to design it so that truss doesn't buckle. It can resist tension or compression. And let's say that we have the choice of either using martensite or perlite. What are the advantages of either of those materials? Well, if we think about a static lateral force pulling on that truss link, well, if we use martensite, typically it's a much stronger steel, it's going to be able to resist a much larger static force, or for a certain level of load, we'd actually be able to use a smaller cross section. But earthquakes aren't static loads. We often think of them that way, but in reality, it's a dynamic situation. The ground is shaking, the mass is being pulled through the truss link to remain connected to the ground. As the vibration increases, the acceleration of the mass increases, thus the force in that truss link becomes larger. If we build the truss link out of martensite, at small vibrations, the accelerations are low. The force in the link is well below the strength of the link. Everything will be fine. But as that vibration increases, as the acceleration grows, so does the force. Therefore, if we make this out of martensite for a certain strength of a link, eventually the acceleration gets so large that the force overcomes the strength of the link. The link breaks, and now the mass is no longer connected to the ground. It's essentially an unstable situation. If we used perlite, then as the vibration grows, the force in being the acceleration of the mass increases, the force in the link increases, but it reaches a point where it reaches the maximum strength of the link, and now the link is going to begin to stretch, but at least it can still resist that force. Now, there may be some permanent deformation to the link. It may be longer than it was originally, and the mass may never return to its original location, but at least it's still connected to the wall, still connected to the ground. So at least it's not reached an unstable point. So because it's a dynamic situation, as the acceleration becomes very high, the perlite's going to yield and stretch. The mass moves from its original place, but at least it remains attached to the wall. The martensite won't allow the system to change or to respond to the earthquake. It's just going to resist and hold that mass in perfect place, but eventually if the force becomes too large, it will just fracture, and then the mass becomes disconnected. Well, the reality is it's very expensive to design structures that are going to be strong enough to resist any size of earthquake without any type of damage. For example, yielding of the link. We only do this for extreme structures such as nuclear power plants or defense facilities. So if we're going to build structures that are not stronger than the forces that the earthquake generates, if we build them with a brittle material, then we run a very high risk that a large earthquake may cause that structure to collapse when things begin to break and fall apart. So if we expect large earthquakes, and we're not going to build the building stronger than what the earthquake will produce, then what's critical to us is the material's ability to deform but remain strong, so that literally we have a chance to ride out the earthquake and survive without collapse. In engineering terms, we're going to talk about that as the ductility. It's defined as the structure's ability to form under large loads. It's oftentimes given the symbol mu, and it's oftentimes defined as the peak displacement that a structure goes through divided by the yield displacement that causes the structure to first yield. One of the goals we're going to see that we're using in earthquake engineering is improving the ductility. Concrete alone is a very brittle material. It has low tensile strength. It breaks relatively easily in shear or in tension. Of course, it has very high compressing strength, but even there, once it reaches its maximum strength, it collapses and has very little ability to deform without crushing itself. The ductility of reinforced concrete is due to the addition of steel in locations where we're expecting high stresses, particularly tension stresses. So therefore, well-designed concrete structures should have the same good seismic performance as steel structures. It's important to keep in mind that we're not saying steel structures are better. We're not saying concrete structures are better. We're saying that either material, steel construction or concrete construction, can result in very good seismic performance in a future major earthquake. So ductile materials, ductile systems, they behave better during an earthquake because they're able to ride out large forces that may develop. One of the relatively surprising ideas is making a structure stronger, but with less ductility, will likely decrease its chances of surviving a major earthquake. By using ductile materials in well-designed configurations, we should be able to survive major earthquakes that produce accelerations far above the level of force that the structure was actually designed to resist. Thank you.